Hi, it's me, your teacher, Kia ora team. Today in this video I'm going to talk about ionic solids dissolving and how we write those equations. I did a little bit of it at the end of my last video, but we're just going to do a bit more practice today, and we're also going to talk about how we can write these equilibrium expressions for these dissolution equations. So dissolution is just a way to say the dissolving of. And for each of these reactions, they are going to split into their two ions. So you're going to have always your metal on the left, or your cation on the left, I should say, and your anion on the right. And sometimes that anion is going to be a whole polyatomic ion. So these are all in equilibrium because you have got some solid that is dissolving while some of the dissolved ions are reforming into solid lead chloride or solid silver carbonate or solid iron iodide or whatever it is you're working with. So these state symbols in aqueous chemistry are really important because they designate what will go into your K expression, which is the same kind of idea across the board. Solids and liquids do not go into your K expression, only gases and aqueous things do. And also because it is an important part of chemistry to show exactly what is happening in your reaction. So my metal cation lead, Pb2+, and my anion chlorine. If you want me to do a video on how to work your ions out, please let me know, but you need to tell me because otherwise I'll just assume that you've kind of got this. I have to make sure that this is balanced. So currently I've got one lead and one lead, but only one chlorine and two chlorines. So I need to make sure I added two up here. Same thing for my silver carbonate. So again, the silver carbonate, your first ionic compound here is always going to be solid before it then dissolves. The whole point is that we're thinking about taking this solid, this ionic solid, and then attempting to dissolve it in water, but it won't dissolve very much because it is sparingly soluble. So we're starting off with solid silver carbonate. Silver has a charge of +1, and therefore because I have two of them, my carbonate must be 2- to match up, and to make sure that this balances I need to have two silvers. So now I've got two silvers on both sides and one carbonate on both sides. And then same thing for iron iodide. I've got iron and iodine. Because iodine is in group 7, it must be a -1 charge. I've got two of them, so I'm going to make sure I've got two on the right hand side, and then in order to balance this out, I need to have a iron 2+ ion over here. So it's +2 plus -1 gives us 0. So that's a happy thing. Here, 2+ -1 times 2 equals 0. And then here, 2 times +1, add 2- gives us 0. Happy. So we always want everything to balance. No leftover charges. So a reminder that these are equilibrium reactions. So as the forward reaction makes ions, the backward reaction is forming solid. Because they're doing this at the same rate, we don't see anything happening with our own eyes or even with measuring equipment of varying, my brain just stopped working, sensitivity. Same rate. So they're happening equally fast, which means that we don't see anything happening, but a reaction is still occurring, and we know that because we can poke it like we learned with Le Chatelier's principle. So because we're able to manipulate it in this way, if we change the temperature, if we add more or less of something, we can cause more reaction to occur. We can push it in one direction or the other, which tells us that it's in equilibrium. These reactions are still happening, because if they weren't happening and the reaction had ended, we would not be able to manipulate them in this way. because it's an equilibrium reaction, we therefore must have a way to write an equilibrium expression, and we'd have equilibrium constant K. So the equilibrium constant for all kinds of different types of equilibrium reaction is always going to be the letter K, capital K. However, we can have a little letter, like here, this S, which stands for solubility. So that tells me that this is an equilibrium reaction that is specifically to deal with dissolving solids. Later, we will look at Ka, which is specifically for equilibrium reactions that involve acids. So A for acid, K for equilibrium reaction. So for this section, we're looking at Ks reactions, or Ks expressions. So we take the same method for Ks expressions as we did for Kc expressions, where C was concentration. So that's just kind of your standard, basic, boring equilibrium. Where K is equal to the concentrations of the products divided by the concentrations of the reactants, where we leave out solids and liquids. And it's really important that you check your answer and also any equations that are given to you in your exam to make sure that they're not like trying to trick you with anything, and look for these solids and liquid state symbols. So down here, we can see a dissolution reaction for a solid lead chloride forming its two ions, lead 2+ and Cl-. So if we were to write a Ks expression for this, it's you have to think about the fact that actually this lead chloride is solid. It's not going to be involved in my Ks expression. The only thing that's going to be in my Ks expression is going to be my products, because my reactants are solid. So in that case, we consider the concentration of the reactant to just be 1. So we assume that the concentration of any solid or liquid is just equal to 1 so that we can kind of ignore it. So that means that I only need to keep the top part of my product. So I only need to think about my ions. So for this one, my Ks would be Pb2+, and the concentration of Cl- raised to the power of its molar ratio. So my Ks, my equilibrium expression, would be the concentration of lead 2+ multiplied by the concentration of chloride ions squared. So this is kind of where it's a bit different to Kc, in that Ks will only ever be your ionic products as part of the expression. You will never be using your reactants, because your reactants will always be ionic solids. So here are some practices for you to do. Give them a pause and then come back for answers. I'm going to give you 2 pauses. So the first one, I'm going to write the dissolution equation, so forming the ions, and then the second pause, I'm going to give you the Ks expression so that you can practice both of those things. So if you get the first one wrong, you won't get the second one wrong. So give it a pause, come back, and check for the equations. All right, I assume you've paused and come back. So again, make sure you've got your, my brain just stopped working again. Why is this happening to me? State symbol, make sure you've got your state symbol. The charge on barium is 2+, as it is in group 2. And therefore the charge on sulfate must also be the opposite, so 2-. Lead bromide, Pb2+, which you'll have to know from memory, or take into account, take into account the 2 Br- ions that are present and add them together. So 2 Br- gives an overall charge of -2, so therefore to balance it out, lead must be a 2+ ion. And then here finally we have got iron and OH-, so OH is always OH-, it's never anything else, and I've got 2 of them, which again will make an overall charge of -2, so therefore my iron must be Fe2+. So give that a pause and then come back for the Ks expressions if you need, otherwise wait 2 seconds and I'll show you the answers. Clap, 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 waiting. Okay, I assume you've come back. Okay, welcome back. I am going to give you the answers to the Ks expressions now. So a reminder that we don't include the solid because it's solid. We assume that its concentration is equal to 1 and therefore we can ignore it. And we only include our ionic products. So the Ks for barium sulfate is Ba2 plus multiplied by the concentration of SO4 2 minus. The Ks for the dissolution of lead bromide would be the concentration of the lead 2 plus ion multiplied by the concentration of the Br minus ion raised to the power of its molar ratio, which in this case is 2. And finally, Ks for iron hydroxide would be the concentration of Fe2 plus multiplied by the concentration of its OH minus ions raised to the power of its molar ratio. That is kind of the end of the stuff that we're hoping you will be able to get through this week. I'm expecting that the making ionic equation part of it is actually going to be the trickiest part. So if that is true, please let me know so that I can try and come up with something to help with that. Cool. All right. Hope you're all doing well. If you're not, please let me know. Like and subscribe. Yep. Kia ora.